First of all, thank you so much for inviting me to speak at this event. I hope, well, my research is quite preliminary compared to the previous two presentations. I hope you could learn a bit more about what is happening within the supply chain analytics area. So this work is on using machine learning to predict hidden links in supply chain. And the idea here is, if you see this particular network on the right side, this is a snapshot of an automotive supply chain network. The color basically indicates a community that were found. We just run a community detection algorithm to see if there's any interesting structure. And of course, these colors apparently correspond to different regions in the world. Some refers to like a network of factory in Japan, some in India, some in Europe, and some in America. And some companies are in between because they interact with different regions, etc. A little bit about me. So I am a second-year PhD student at the University of Cambridge, Institute for Manufacturing. I focuses mostly on supply chain analytics as well as risk modeling. And the approach that I've been using these days is mostly graph neural network, because I've shown that through this work, it improves a lot compared to handcrafted heuristics. And I'm also interested in any network science concept in general, because like supply chain in the past has been seen as this linear structure, but we know through a handful of studies that supply chain is actually more like a network instead of a chain. And we've seen in recent cases where disruptions happening in one place could propagate throughout the whole network, just like how a disease could propagate epidemiologically. And yeah, I used to work in the industry for a company called Keysight, and we were in the manufacturing sector. So I have hands-on experience on dealing with supply chain problems firsthand. Now, a bit about the background behind this research. Allianz, which is one of the biggest insurance company, they release this risk barometer report every year. And for the past 1 decade or so, contingent business interruptions, including supply chain, has been one of the top global business risk. It's always either in number 1, 2, or 3, but this year and last year, it has risen up back again to the top 1 global business risk. I just took a couple of snapshots of recent supply chain disruptions here. I mean, some pictures here were taken from a decade ago, disruption in Thailand, flood, as well as tsunami in Japan, sort of affected the whole industry, even though, many companies say in the UK or US might not think that they're connected to the suppliers, but apparently after a disruption hit onto that region, a lot of companies are affected. I mean, closer to where I am based in the UK, we saw a couple of disruptions as well in soft drink and supply issues. The UK is now facing a bit of a gas shortage. And you must have also heard of the Suez Canal disruption. And so the common story behind all of this is, a company that is based maybe in the West or somewhere else, even though in the past you think that you are safe from any of the disruption that is happening outside, that is not true anymore, because the supply chain is a complex network, and hence you need to have more visibility over what is happening. And so supply chain stakeholders would now like to understand how is their company exposed. Based on a survey that we are doing, this is another qualitative study that is on progress. We speak to different players in the supply chain. Supply chain managers would like to ask questions like this. Yeah, if a particular supplier X at tier Y, which is basically how many hops away are you from me, is disrupted, with what probability would my company be affected? This is a question of risk propagation, basically. And in terms of insurance as well, so my PhD is funded by a company called Aviva, which is one of the biggest insurance company in the UK. And the questions that they are interested in is to see, if I insure a company called John Doe and John Doe goes bankrupt, which of its buyers would be affected? This is the kind of questions that insurance companies would like to ask. Of course, this is in a simplified manner. There are way more questions that people would like to ask. And bottom line is, we see that many of these questions could be formulated as a first order logic queries, and if I simplify even further, those first order logic queries could be broken up into a bunch of conjunctions of these kind of questions. Well, if I want to know which of John Doe's buyers would go bankrupt, then I could convert this as an inquiry whether there is a hidden link between, say, John Doe company and another company called Company X or Company Y, etc., etc. And XY would be a placeholder for a company name. Well, first issue that you might see here is that if there are 10, 20, 30,000 companies in the world, then you might need to run this model for every single one of them. This is also another question that is pending. We will need to further explore how to reduce the size of search, again, because the number of companies could increase infinitely many. I mean, some recent approaches, I didn't use it in my work, but some other recent approaches that you could do is, if you convert each company and its topological structure into an embedding, then instead of doing, you could focus on the embedding and just look at nearest neighbors that are like in the embedding space. So the search now becomes on the continuous space, on the embedding space, instead of the more discrete graph structure. But I'll go back to this point. The point here of this slide is that some risk questions could be treated as an inquiry on the existence of a hidden link, and hence this becomes a link prediction task. Now, before I go on to the link prediction task, if I model the supply chain as a graph, so this is a real supply chain data. If I model this as a graph, then the question becomes, if I pick two random nodes, can I predict if there's a hidden link between the two companies? Now, the reason why this is interesting is because in supply chain, there's this known problem of visibility. So one of a senior from my group, he designed an NLP technique to, read news, say from Bloomberg or Icon, Refinitiv, etc., and then try to extract supply and demand, supply buyer relationship between companies, convert them into triplets, and then create a graph out of, this relationship. But we found out that many companies are hiding their information, and hence, even if you do this, your graph will be incomplete, and you need a way to fill in the missing links in the graph. And this was a big problem that is facing now inside the project. So the question becomes, how do we predict the missing link? Now, this is at a high level perspective. This is what the result would look like. I will explain in more details how we did it. So before link prediction, this is how an ego graph of Ferrari would look like. An ego graph basically means if you take a graph and then you take a one-hop neighbor of the particular node, this is how the surrounding subgraph looks like. See, there's just like a company called Ferrari would have information about some of these nodes. But if we use graph neural network to identify hidden links, apparently there are more and more hidden links that were not found in the network. Companies like Johnson Controls, for example, who might not be, if Johnson Controls, Ferrari wouldn't have thought that Johnson Controls would be a big supplier, but apparently they are quite well connected to all of the other suppliers of Ferrari. So maybe these companies are those that Ferrari would need to pay attention to. Before graph neural networks, there has been some handcrafted heuristics approaches to doing this, but they were not too robust because, again, as with any heuristics, you need to properly define what sort of measure are interesting or what sort of node should you be looking at. And these are just to customize. And our approach here is more automated. And the way I approach this is, so there are many ways to do link prediction. The one that I work here is based on a model called SEAL, which was published in NeurIPS, I think in 2019, NeurIPS 2019, if I'm not wrong, from Wuhan, and he's now in Facebook. The idea is, if you take two nodes, node 4 and node 56, node 4 could be Ferrari, node 56 could be some other nodes. To take the two nodes, take the subgraph, I can relabel the subgraph using this algorithm called double radius node labeling. And the basic idea of double radius node labeling basically is every node is colored, and the color of every node is determined by the shortest path distance between that node and the two links. So now you could see, if I add a pointer, and So if you see at this graph, second graph, you'll see that the graph has been recolored. And now you see like most of the nodes are colored with 2, 3, or 4. That means they are, 2 hops away from the red node, or 3 hops away, or 4 hops away. And this information would be sort of a topological structure that would represent this whole graph. And I could then create a matrix whose dimension is nodes times number of maximum color or label that one could have. And then this would be sort of a feature for this subgraph. Now, the reason I have to extract this feature for this subgraph is because sometimes if you work with certain graph, you might not have any information of each node. So you need to sort of build an embedding for the node, an initial feature, basically. You could have started with a random embedding as well. That's also fine. Because anyway, graph neural network will sort of capture some topological information still. There's a paper on, I think, that basically proves that graph neural network is like a hashing function. So even if you start with random embedding for each node, if you run graph neural networks for a few layers, then you could still capture some topological structure. This is just an additional information that has been shown to work quite well. The next step. So for embedding, I'm just answering question to Marco. So the algorithm that I use for embedding is, hold on, Calvin, are you hearing background noise from my side? Just to check. So for Andrea, the question on embedding, like the initial embedding that I used is this double radius node labeling. But then in order to obtain the final embedding from the graph, I still use graph neural network. So graph neural network will do message passing to sort of aggregate information from the different nodes and then form it into an embedding. Now, sorry, this picture is a bit blurry, but what happens is, see, so now I sort of have this embedding on the graph, and then I can apply to graph neural network. I did not include the equation here because I think it has been shown by Charlie in the previous slide. Basically, it's just a bunch of message passing, and then I'll get a representation for every node in the subgraph. And what I'll do next is I'll pull them into one embedding, this orange color vector that would represent the original graph. So now I have converted a link prediction task into a graph learning problem. If I take a subgraph surrounding a particular link, I could convert them into one vector of m dimension. And then I can just fit this into a fully connected network to decide if there's a link or no link. And we found out that by using this approach, our result outperforms and graph heuristic. So if you happen to have time, if you look at the literature of supply chain link prediction, there was one work in 2019 called SNLP, which was like the state of the art. And I have to say that not a lot of people look at link prediction for supply chains. So that was the only state of the art that we had. We improved, if you see here, blue line compared to green line, we improved quite a lot in terms of area under the receiver operating curve, as well as the average precision. And we try this for different test ratio, because one of the important key about link prediction is deciding the ratio between the number of negative samples and positive samples. If you have way more negative samples than positive samples, that would affect your precision, because now, well, it's basically an imbalanced data set. And it also makes the problem more challenging. Now, what's more interesting is, instead of stopping there, I also try to do a bit of analysis to interpret the network. So in typical convolutional neural network, we know that there are different approaches to extract what is it that the model is looking at. And one of the most famous one is called integrated gradients. So we also use this for our graph neural network model. The basic idea is, for every edge input in the subgraph, if I sort of change the value, how would that affect the output value? Yeah? And if you look at the equation roughly, is I'll change the input index by m steps, and I'll observe how much would that change the output of my value. Will it change my output from having link to no link? And this, in a sense, became a bit more like a sensitivity analysis problem. And what we found out is, by using this method, I could identify, within a given subgraph of a link or a pair of nodes that are of interest, Then those nodes that are highlighted with darker colors are sort of the edges that are more important. And as you can see here, for an example, when I'm looking at a potential relationship between a company called Lear and a company called Guangzhou Jixing, you could see that it makes quite some sense. Like the model is looking at edges that connect the two nodes here. So it's not surprising. You could also see here for Magna International and Wuxi Plastic Hardware. You also see that it places more emphasis on edges that represents these two nodes. What this means is if I sort of remove an edge that whose color is quite light, that wouldn't affect the output prediction. And this is quite useful for anyone who wants to play around with the model. But of course, like the model is looking at different things. Sometimes it's not completely explainable. So I must say, like, explaining an explanation is also an open task that one would need to look at. Now, that work was published in a supply chain journal, and hence using that we can answer questions. The original question, predicting links, hidden links between two companies. Yeah, as I said, that was published in the journal, but we did not stop there. We went on and thought, hey, you know, we've been working with a homogeneous graph. What happens if we now start to look at a heterogeneous graph? Because we know that every node in supply chain, every company would have different information, like, you know, what are the capabilities that the company has? What products does the company make? What are the certifications that the company owns? Who is the owner of the company? Where is the company located, etc., etc. Now, this information, we could, you know, convert them into a knowledge graph or a heterogeneous graph. This is an example snapshot here. Just took like 5 companies just to show how it will look like. And the next, what we did next is to adapt our graph neural network so that it works with a heterogeneous graph. Again, there are a lot of different ways to do so, but one of the most straightforward one is to simply have a graph neural network for every type of edge on the graph. Now, this is known beforehand because, like, we could work with companies to define an ontology of the knowledge graph, and ontology simply means, you know, what sort of what type of edges exist, what type of companies exist in the heterogeneous graph, and then yeah, we could run another model on it. So the model performs quite well. We publish it in ICML workshop. I'm now trying to convert this into a journal paper, adding more information. So if you have any thoughts on feedbacks, or if you heard anything about usage of knowledge graph in supply chain, do let me know. I'd be keen to hear more from you. Yeah, and for anyone who's been following graph neural network, the good news is if you use PyTorch Geometric, PyTorch Geometric has recently released a second version, and in PyG 2.0, they actually support heterogeneous graph by default. It's a first-class citizen, so quite useful for anyone who wants to look at graph neural network. And yeah, I must say my presentation is quite short. It's a work in progress, and I would really love to hear any feedback from you. And again, thanks for giving me the opportunity.